Module 4, three-phase fundamentals. Let's see what the topics are here that we're going to cover here. We're going to explain voltage and current phase angle relationships of three-phase loads. We're going to explain how to calculate single-phase and three-phase power. We're going to explain the differences between the three types of electrical loads, resistive, inductive, and capacitive, like we did earlier, but this time associated with three-phase characteristics, as you would see in the power system. Discuss per unit system with that's used in a three-phase power system and its purpose. And we're going to start out here with Faraday's law. Now, this is a review because the three-phase system starts out with a single phase. So what we learned in AC fundamentals earlier is going to be applied now to three-phase. So Faraday's law is a voltage is produced on any conductor in a changing magnetic field. And you can see by spinning the magnet, we produce an AC sine wave. Now, when we put three of these coils together with one spinning magnet, we produce three-phase voltage. Same Faraday's law. This time, we have three separate generators, if you will. Three separate single-phase generators. And since it's 360 degrees in a circle, they're all 120-degree phasing. They're all offset by 120 degrees. So you can see how the three sine waves kind of make up time very efficiently. And this is basically what we're having. We have a three-phase generator that is producing three-phase power in real time. And that's one thing about a three-phase power system is that these generators are producing power and we are consuming power in real time. We're not storing any three-phase. We're not saving it up for later. We're just operating it as we generate, as we load it up. So our generation is really adjusted by how much load we have. So as people are turning on and off light switches, the generator is ramping up or ramping down in the system. So it's all real time. Okay, now let's look at the second physics law where we are talking about the current through a wire will produce a magnetic field. So here we have a coil and we put a current through it. Now this is DC current. We have a battery there and we're putting DC current right through the coil of wire and we're producing a north and a south pole. Okay, now the slip rings has to do with how this electromagnet is basically connecting to the outside world. When the rotor itself or the magnet itself is spinning, we're going to have slip rings, and I'll show you more on that here in a few minutes. So we have the coil producing a magnetic field, and that's what you're seeing here. So as we have current flowing through the wires, we produce a magnetic field. If we reverse the battery polarity, the current would flow the opposite direction, and then our north and south poles would reverse. So if we had an alternating voltage here, we would get changing magnetic field, and that's an important concept. Now, taking it a step further, in a generator's rotor, we might have a north pole and a south pole, which is made up with the coils. We're using electromagnets, not permanent magnets on big generating systems. So if we had coils of wire, we could increase the number of coils so that we can have multiple coils on a rotor and cause the rotor to only have to spin half as fast, in this case where we have 4 poles. So if we have a 2-pole rotor, our generator normally spins 3,600 RPM. If we have a 4-pole motor, it will now spin 1,800 RPM. So as we increase the number of poles, we decrease the speed because we have a north pole coming back around to be a north pole in half the time. So our speed of the shaft could be reduced in half. And if you take a case like at Boulder Dam or out there just outside of Las Vegas, they have generators there that run 40 poles, which means their shaft speed is roughly 3 revolutions per second. And you can actually watch it turn. It's about that fast. Because they have so many poles, it doesn't take very far to have a north pole go through the red, the blue, the green phases, the red, the blue, the green. It comes up so frequently that the shaft speed can be much slower. So I just want to point out that shaft speed can be controlled by the number of poles on the rotor. So here we have a drawing that shows a stator, which is a stationary part of a generator, 3 coils, 3 stator windings, that's representing the 3-phase, 1 electromagnet that's producing the north and south pole, which is being turned by a prime mover, but it has slip rings connected to the shaft so that the 2 wires from the coil can be connected to the outside world, or the non-spinning, the stationary side, through slip rings, which are almost like disc brakes on a car, but you're making metal connection, making metal contact, electrical contact here through the connectors, through the contactors, and then you have a DC supply. Now this area here is referred to as the exciter, the stator, the rotor, which is sometimes called the field. Okay? So this is the basic parts of a 3-phase power system voltage generator. Now, there are 2 ways to hook up the 3 coils, 6 wires, symmetrically. The Y and the delta. So if we were to connect up the 3 stationary windings in a delta configuration, it would look like this. We'd take a wire from 2 windings, and that would be one of the output wires. We take a wire from these 2 windings and an output wire, these 2 windings and an output wire. We actually produce a delta with the 3 windings. Or we take 1 common wire, 1 from each winding, each coil, each winding, form a neutral, and then the opposite end of those windings become the output wires, if you will. And the neutral is then grounded. So we'd have a grounded neutral. Note, there is no neutral in a delta. Now that's good and bad, okay? The fact that you have a neutral in a Y adds a lot of benefits, especially in distribution, where you have a neutral, a multi-grounded neutral, and if it's grounded and earth is conductive, that if you dropped a wire, if a wire fell from the structure down to the ground, you'd cause a ground current. Because the system is grounded, you get a ground current, you can sense the ground current and trip the breaker and turn off the fault. In a delta, if there's no neutral and a wire hit the ground, nothing happens. So you have issues where, where does the ground current go when you have a delta system? There's advantages with delta. Deltas eliminate 3-phase harmonics, the 3rd order harmonics, and consequently improve power quality. Talk about harmonics later. The Y system, the grounded Y, allows you to have better voltage control over each phase. It's easier for protection purposes. Fuses, 1 fuse will blow. In a delta system, you might have multiple fuses blow on a fault. You might fatigue a fuse. You don't really know. That's kind of the issue. So in a delta, you only have 3 wires instead of 4. So there's advantages and disadvantages, but you'll find that most of the time we have the grounded Y system in our distribution services and what have you, and we run delta in transmission, but we also run in transmission what's called grounded source Y. It's even another configuration. Grounded source Y means that a transformer might be connected up as a grounded Y, which has a neutral grounded and all, but the neutral is not brought out on the transmission line. It's assumed that the 3 phases are equal current, you don't need a neutral, and what have you. So even the sources might be grounded, or a source might be grounded, but not necessarily run 4 wires on the transmission line. Okay, so there's a little variations, but the main point here is that there are 2 ways to connect the 3 coils symmetrically, and that's the Y and the delta. One has a neutral, which is grounded, and the other one does not. So just know that. Okay. Now a little bit on the mathematics here with 3-phase. We use the mathematics, at least in here, not necessarily to question your ability on solving mathematical problems. It's to show relationships and to help explain complex concepts in simple to understand terms. Like when we talk about Ohm's law, or we're talking about, you know, some of the math, we're not really drilling hard on the math. Just want you to understand the concepts, okay? So when it comes to power, we have power is equal to the current times the voltage. And for the example there, we have power is equal to 10 amps times 120 volts, or 1200 watts. I mean, that's pretty simple. That's single phase or even in DC. Okay, when we go to three-phase, this is still another power equation. This is Ohm's law, where voltage is equal to current times resistance, and power is equal to current times voltage. Those are the two fundamental laws. And we touched on this earlier, so this is kind of a review. But here is where, if you take power that is equal to the current times the voltage, and you substitute the fact that voltage is equal to current times resistance, IR, into the power equation, you get the I squared R. And remember, we were talking about that in the AC concepts, that power is also equal to I squared R. Well, this is where it comes from. Substituting Ohm's law into the power equation, coming up with I squared R. Okay? Actually, I want to go back on this. One other part, too, is this equation, power is equal to current times voltage. That's also the formula for a transformer. It's important for transformers because the power into a transformer is equal to the power out of a transformer, neglecting losses. So when you have on the input of a step-up transformer, it's low voltage, high current. The output is high voltage, low current. But voltage times current in equals voltage times current out. That's what makes transformers so valuable and useful. And yet we like to know about the I squared R losses because that's what controls our cost. Okay, now when we come to three-phase power, there's a square root of 3 thrown in there. Okay, so you can see where the square root of 3 times the current times voltage. So you would take the line-to-line voltage and you would take the current in one of the lines, and that would give you your three-phase power. So for example, if the numbers we used earlier were a three-phase system, then we're talking about 2,078 watts because of the square root of 3. Okay, so three-phase just means there's a square root of 3 in there. That square root of 3 comes in a lot of different places. It could be, you know, line-to-line voltage on a transmission line versus line-to-ground. There'll be another square root of 3 in there. So we're going to use the concepts of there'll be a square root of 3 now and then in some of the analysis, but that is, you know, the difference between three-phase and single-phase. Okay, so again, with a little bit of the summary of the math where we have energy is equal to power times time, which is the same thing as watts times hours. And when we have an example of a 60-watt light bulb that runs 100 hours, you know, how much energy is consumed? We would say that 60 watts times 100 hours is 6,000 watt hours or 6 kilowatt hours. And that would basically tell you if you had a 10-cent energy rate, that would cost you 60 cents to run a 60-watt light bulb 100 hours. Those are just a little bit of fundamentals. The factor of 3, square root of 3, does not come into play here when we're talking energy. When we have a 60-watt, you know, hours, and we're talking about this happens to be like single-phase load. If you were to use three-phase load, then there would be a factor of square root of 3 in there. Okay, here's what gets kind of important for complex situations trying to be made simple. Here we have the 3 basic electrical loads, the resistance, the inductance, and the capacitance, and with the ohms, the henries, and the farads, and the symbols, and the types of loads pictured there. But if you see resistance, you know, like a toaster, a light bulb, a heating element, a hot water heater, what have you. But electric power systems, actually this is what's called a braking resistor used at Bonneville Power, and it's just conductors going to ground, that if a line were to trip and we would have excessive generation, this braking resistor would get switched onto the system right away to put load on the generator so the generators don't go running very quickly, very fast. Because you take the load off the generator and it wants to spin really quickly, just like when you're in your car and you're driving along and you take the car and put it in neutral. Your engine wants to really rev up. So the braking resistor keeps it from exceeding its speed so that it doesn't trip off from protective relays. So there's resistive load there. It'd be one heck of a heater if you kept it on. Now you have inductive load, which is anything with a motor in it or a coil, okay, where you have lagging current. The current lags the voltage. And we have transformers at the bulk power system. Capacitive loads, where we have capacitors. You saw the little simple capacitor on a circuit board versus capacitors on a power system. And we'll talk more about capacitors later. But I want to talk to you about the relationship between voltage and current in these as it applies to, three-phase power systems. So first of all, we have resistance, inductance, and capacitance, all running with AC sources. Now, here's the phase angle we talked about earlier. You have a voltage, which is your reference. Remember, we'd like to choose voltage as reference because that's where our generation kind of starts. It starts with the generator. And our current. And our current is lagging, which is indicative of an inductive load. Okay? And there's a phase angle between the voltage and the current. Okay? So we're kind of reviewing a little bit of the concepts we've already covered. But now let's look at the relationships with load. Here's resistance. Here's where the current and the voltage are in sync. Here's inductive, where the current lags the voltage. Okay? And then here's the capacitance, where the capacitive circuit, where the current leads the voltage. Okay? And we talked about if you can add a capacitor and an inductor together, you can cancel it out and make the circuit look resistive. Okay? Now, looking at this a little bit in kind of a real time, here's the current at the time of peak voltage, which is very important. The current at the time of peak voltage is the real power. That's the watts. Okay? We spoke about peak voltage and peak current, where the peak current is up here or here. When it's a peak voltage and peak current, that's the VA. Remember the VA, the hypotenuse of the impedance triangle, the VA? Okay. So the main factor here is this is the current we need to produce so many watts. If we had a 100 horsepower motor, we would have this current at peak voltage, but it would draw more current because it's lagging. So we have a higher current so that the current at the time of peak voltage is the 100 horsepower. So we're running a higher current than we need. If we could add capacitors, we could balance this thing out. Okay? So that's the idea here that's going on in the power system. So when we look at the power formulas again, we have the power is voltage times current. Power is, total power. The hypotenuse, the VA, is peak current times peak voltage. And then we have the real power. This is the current at the time of peak voltage times the voltage. That's the watts. So now when we look at the total power, we have real power, the real power squared plus the reactive power squared, and that gives us our total power. But we're in the power system, we're looking at the real power in watts, the total power, which is the watts and the VARs, and we're trying to work with the VARs to not be excessive, but you want to have reserves so that if you have outages, you can have a stable system. But in order to understand some of those power system dynamics, you need to understand these simple terms. Okay? Now, taking this a step further, if this is the current at the time of peak voltage, and this is the real power, the watts, and we are lagging so much, then if we could add, back up, if we could add a capacitor to to move this forward, a capacitor causing leading current, we could have the peak current will only become as high as the load requirements. It's a little tricky, a little hard to explain, but right now, if we take an example of a 100 horsepower motor that's running at peak, it's going to have a certain current demand when the voltage is at peak. But the current goes up because it's lagging in order to get us the current we need at peak. If we added a capacitor to it, we could move this peak and it would come down like that slide, that animation I had, and our current would only have to be that much. The savings in current would be the difference between this level, and that savings in current squared is the savings in losses. So you can see how much that is helpful. So now when you look at this, if this is the voltage and this is the current, then current times voltage is power. Power is here. Now, since this is time, little quick note, if this is power, what's underneath the power curve? What's all this area underneath the power curve? The area underneath the power curve is what? Energy. So if you want to think of energy, energy is the area under the power curve. Okay? That's because it's times the hours. So here's our peak watts going on like this. Now, what happens if we have leading or lagging? Well, in this case, we have capacitive, and in capacitive, we have leading current. Okay, here's our voltage here. And this, when the voltage is positive, the current is positive at this point only to this point, and then the current's negative here. This is the part that's positive power. Here the current's negative when the power is positive, and a negative times a positive is a negative. So now we have negative power here. Then we have positive power negative power when you extend that over. So you can see we're losing on power because we have a leading condition. And if we had inductive or lagging, the opposite is true. We have, here's our voltage is positive, our current is positive, that's positive power. Our current is positive, our voltage is negative, so we have negative power. And it repeats itself. Okay, so I guess to summarize, I don't know if I have to start over. I'm taking a little break here because when I clicked it, it skipped a slide. I went to capacitive first instead of inductive.
Whatever flows best for you, I can just make a note here to switch those out.
The slides aren't a big issue, I think, but you started talking about one thing before you started talking.
As long as I know what your intended flow of the slide is.
Well, see, now I want to kind of summarize this before I go to the next slide.
Why don't you just start? It's fine. It's a pretty important slide, so.
Just back it up.
Yeah, just go back and start from where you think.
This is where it was fine.
Okay, so that's fine. Transition from this slide to the next.
Yeah, I went to capacitive, but it should have gone to inductive, and I only clicked it once, so it was a weird skip.
No problem.
All right, so I just finished while they're in sync.
This is good stuff, by the way.
It's helpful, yeah. Okay, so I'm going to start this over. Okay, now here we have the case where we have inductive load. Inductive load, as you remember, the current lags the voltage. So what happens here in the real world? We have voltage here, which is our reference, and current lags. So if the current lags, our voltage is positive and our current is positive here. So a positive times a positive is a positive. Now here the voltage goes negative, but the current's still positive because it's lagging. Here we have a positive and a negative. A positive times a negative is a negative number, so we have negative power. Then we have positive, we have a negative current and a negative voltage. A negative times a negative is a positive. So we have positive power. and negative power. You can see that when there's a lagging condition and a leading condition, we end up with negative power, and that's the part that is problematic. You know, we want all the power, okay? So let's look at it capacitive. In a capacitive circuit, we have the current is leading the voltage. So here's the voltage, and here's the current. But now where the voltage becomes positive, the current is positive, so a positive times a positive is a positive. And here we have current negative, voltage positive, and negative times a positive is negative. And here we have negative times a negative, which is a positive. And we go on. The idea here is if we can put enough capacitors on a lagging system, we can zero out the phase angle between leading and lagging to allow power to equal voltage times current. It does a lot of things. It lines up the voltage and the current so that at peak voltage you have peak current. When you have peak voltage and peak current, you are all watts. That makes it 100% efficient. No negative power. That's what's very important. When you go leading or lagging, you are doing a couple things. More current. Well, more current on a system, what does that do? What does that do? It causes more voltage drop. Well, what does that do? It gives you voltage collapse if you're not careful. So we're trying to minimize VAR flow to minimize current, which minimizes the losses, which minimizes voltage drop, which improves voltage stability. I hope all that kind of comes together because that's really what the crux of all this is on a three-phase power system. Okay. We're going to talk a little bit about the per unit system. The per unit system is a simplification process of working with big numbers and trying to make them easier to work with. This is more of an engineering aspect of power system analysis, but it's very important. When you're on a per unit system, you have base voltages and you end up with a system that is a little easier to analyze. And if any of you are planning to become, system operators or get into system or engineering, you'll come across per unit system. And what we're doing is it's basically a ratio system. We're just kind of setting up a ratio. If everything's at the same voltage, then let's just use that voltage as a base, and then we don't have to. We just multiply that back in at the end when we're all done with our analysis. So our numbers are a lot easier, and at the end, we just multiply by the base, and we get back to the reality. So that's kind of, in a sense, what per unit is. So going through this, we're taking multiple voltages and we're creating a system that has multiple voltages like distribution, transmission, through transformers, whatever, and we're setting up a ratio system. It's mainly because we have a lot of transformers, and the transformers and the currents and the voltages change because of the turns ratios of the transformers. And, until we get to the numbers that we're really looking for, the answers, the results, we're going to switch into like a transform into a per unit calculation and then convert back at the end. So for example, which is more meaningful to you? The current in a line is 200 amps, or the current in a line is 98% of rated current. What's more important to you? Well, first of all, if I said 200 amps, you have no idea what the maximum is. Is it a 400 amp max line? Is it a 2,000 amp max line? Is it a 100 amp and we're double the power or the current flowing through it? The first one doesn't give you a lot of sense, but the second one does. It's 98% of the rated current. That tells you a lot. And when you look at simulators and when you look at drawings and you look at analysis or power flow diagrams and you see what's going on, it's more important to you to know if you're close to capacity or not. And that's kind of where the per unit system comes into play when you're a system operator. Okay, and some of the basics behind a per unit system is, we're going to present all of the numbers in ratios. So with the impedance, and you have that in the power, and those things are all, still the same. The current per unit would be the current divided by the base current, And same with the power divided by the base power, or in impedance, the base impedance, and the voltage of the base voltage. So you're really saying, all right, let's establish a base voltage, a base current, a base impedance, a base power, and let's just keep everything in terms of a ratio. And we pick the bases. If it's a 25 kV system, we'll let 25 kV be the base voltage, for example. And then everything kind of becomes ratios. All right, so only 2 of the 4 variables are independent, okay? So we have, you know, we say voltage, current, impedance, and power. So current equals complex power, watts and vars, divided by voltage. Because current is power divided by voltage, so current equals the watts and the vars divided by voltage. So that kind of sets up a ratio there. The voltage is, you know, we have the complex resistance and reactance multiplied by current. Voltage is resistance times current. So we're going to have that as a ratio. Then we have complex impedance equals voltage divided by current. And we have power is equal to voltage divided by current. So because power is voltage divided by current, or current is power divided by voltage, you know, we have redundancy in there, so we don't need to have ratios for everything, is the point. You only need to do 2. All right, so the usual procedure is to take complex power and voltage as the basis, okay? They're the basic units. You know, what is your power? Is it a kVA? Is it an MVA? And what is your voltage? Are you on a 230 kV system? You know, that type of thing. And then calculate the other 2 variables. For example, assume that all the transformers are ideal. That means no losses. Then base power is constant from source to load, right? Power into a transformer is equal to power out. Power is the same, but the voltages are determined by the turns ratio. So we have to have different voltage bases depending on which side of the transformer you're on. So taking that into consideration. Now, because of the different voltages of bases and the power is the same on both sides of a transformer, we set up a per unit basic system that looks like this. You have zone 1, zone 2, zone 3, and etc., where the voltage is determined by between the transformers, where the power we know is the same going through. So look at the notes. There will be a different base voltage on each zone of this diagram, and with ideal transformers, the per unit voltage in each zone takes care of the turns ratio. See that? Now, so we can assign any transformer impedance to the line characteristics and the transformers disappear. So we can just say, all right, for the different zones, we have the different voltages, and we don't care about turns ratios. We'll just give an impedance to give it look like a resistance, and we're good. We can solve these problems so much easier. Now, I'm not asking you, or we're not asking you to calculate per unit. No, that's not the goal here. The goal here is to understand why per units are being used. It's so that we can have simulators and programs and displays that tell you it's 98% loaded or 110% loaded, you know, because we put impedances in for transformers, we put impedances in for the transmission lines, and we look at the power and we measure the power, and we can calculate, we can predict, we can use state estimator and come up with some solutions because we have this kind of a model. So the whole idea here of three-phase fundamentals, to talk about, you know, the basics of per unit, is to make life easier for the operator and for engineers excuse me, trying to analyze a system. Okay, let's summarize what we've learned in Module 4 with the three-phase. Okay? We explained voltage and current, phase angle relationships of three-phase loads. Remember how we have the leading and lagging the current, and we're trying to balance that out so we can minimize current and get that current minimal so we have the fewest losses. And actually, if you have a conductor that's good for so many amps, let's say 1,000 amps, like 795 ACSR or something like that is close to that, or 1,200 circular mill type conductor, where it's good for 1,000 amps. Well, if you're running 800 amps in a 1,000 amp rated conductor, a couple things to know about. Number one is if we can reduce the current, we're obviously going to reduce the I²R losses, and if we reduce the current, that gives us more capacity available to hook up more loads. Okay, so there's a win-win. We would love to load up the conductors to 100% if it's all watts. If we got VARs in there, we don't get paid for VARs, remember, generally speaking, so we want to try to run it as efficient as possible. Okay, so we talked about those relationships. We explained how to calculate single-phase and three-phase power. Remember that square root of 3 comes into play. We explained the differences between the 3 types of electrical load: resistance, inductive, capacitive. The types of load, their characteristics, the leading and lag, again, with respect to power, current, and voltage. We talked about the per unit system used in three-phase power and its purpose. Remember, we were showing how we simplify, and we can create power system simulators and programs, which you're going to be able to use later on. That'll you'll see the percentages, and when we're running out of capacity, it's all based on per unit and how it's done. Give you a little bit of insight into that. So that basically covered this particular section on three-phase power systems. Now I'm going to switch over to the dry erase board, and I'm going to show you what we've learned in a three-phase power system from generation, transformers, transmission, transformers, distribution. We're getting to the feeders, and you'll get a concept of what's going on here in the power system. So I'm now going to switch you over to that. Okay, I'm going to introduce you into a handwritten three-phase power system now that we've got to this point. I think you've got enough fundamentals now that I can draw a power system here on the board and start to relate, because further on we're going to get into equipment, we're going to get into high voltage equipment and all of the pieces that kind of make this happen. But let's start with the generator. Here we have a generator. It's a three-phase generator. That's the stator. Okay? And in the generator we're going to have 3 windings. We're going to have the red, blue, and the green. So if I have the first winding is going to be the red phase. There's 2 wires out of there. And I'm winding it this way. Okay? And then I have the blue phase, 2 wires. Okay, and then I have the green phase. This is over here. 2 wires, and behind there is the 3-phase. In the center, we're going to have the rotor. The rotor is providing the north and south pole. It has a north pole, south pole, and then there's a shaft to it. Okay, that shaft is going to come out here, and we're going to spin that shaft. But if this were a permanent magnet and I spun this shaft, I'd be generating electricity right now. But in the power systems, in the big generators, we don't use permanent magnets, we use electromagnets, which means we're going to have a coil of wire. Okay, and that coil of wire, if I put a DC current through that coil of wire, I'm going to have a north and a south pole. And the 2 wires kind of stick out on this end. So now I'm going to put slip rings. Okay, and another slip ring. Okay, I'm going to take one wire connected to this slip ring, the other wire connected to this slip ring. I'm going to have some brushes touching the slip ring.